Well, hello, pre-calc. Welcome back to Chapter 1, Lesson 1.2 on graph properties. So, start up with a little warm-up here, and we're going to be looking at the equation of a circle. Remember from last year, this would have told you that this circle is centered at the origin at 0, 0 because there's no adjustment to the x, no adjustment to the y. And this is the radius of that circle squared. So normally what we had to do is we had to solve this for y equals in order to be able to put it into our calculator and graph it. Okay, so what we would do is just solve this for y. So the first step would just simply be to make this y squared equals r squared minus x squared. And then we'd end up just square rooting both sides. All right, and we'd have y equals, and if we normally would get a plus or a minus here for the top part and the bottom part of the circle, but if we just look at the positive part at the principal roots, this would be r squared minus x squared, and that's how we would be able to put that into our calculator. And in this case, the parent function for a semicircle where the radius equals 1, that graph would just be something really right here, just be that upper part of the circle. Okay, that's the positive part. So you could end up looking at that if you wanted, if you had a radius of 1, you put 1 in for r, so it would be 1 squared or 1 minus x squared. And we could even do the old school, graphing in terms of just making an XY table. And if you put negative 1 in for x, this would end up making that 0. If I put 0 in for x, that'd make it 1. If I put 1 in for x, then make that 0. And that's how we get those points right there. Okay. If I look at just graphing this one by hand, I would know here that's my r squared. My r squared is 25, so I know my radius would have to be 5. And I would have a semicircle that would go like this. Okay. Again, you could do that with a table of values, looking at that to help plot this if you want to really go old school on this. And say that if I were to put, say, negative 5 in for that x and get 0 up for y, because negative 5 squared is 25. 25 minus 25 is 0. Square root of 0 is 0. I could put 0 in there and I'd get 5 out. I could put 5 in there and I'd get 0 out. So just kind of remind you a little bit about semicircles. All right, well, let's look at some new things here. We're going to look at some graph properties. And first kind of vocabulary word we're going to have here is the word continuity. Okay, continuity. And then as well, we'll have discontinuity. Okay? So obviously opposites of each other. What I like to think about with continuity is that the word continuous. And referencing it to graphs, I like to think about it as if I can put my pencil on the graph and never have to pick it up. I can continuously graph the graph without picking up my pencil. The only thing I'd say here is you probably should have some arrows on the end. So going on forever, I don't have to pick up my pencil. Discontinuity occurs when I have to pick up my pencil. All right. So if I look at this first one, I'm kind of starting here, going along, and I hit a hole. All right. That's, if I look at that, there's that open circle right there, which means I can't touch that. And there's actually a little hole in the graph right there. All right. The actual value for that spot is actually up here. So we'll talk about removable discontinuity at the end of this lesson. So that's actually, just as a preview, that's a type of removable discontinuity. But right now, we're just looking at that there's a hole in the graph. And same thing here, there's a hole in the graph, but there is no corresponding value to replace that hole. So again, this is just called a hole. All right. So it's discontinuous, and it has a hole at this point A. In this example right here, again, as I'm kind of drawn along, I hit this and got this hole, and then I kind of have to jump up to here to be able to continue along on that graph. So this is actually called jump discontinuity. Because actually you have to kind of, like it says, just kind of jump up to where you couldn't touch, and you could jump up, and it's right above, or it could be below too, where that point where that hole is, where that discontinuity is. And then the last example of discontinuity is actually an asymptote, and you should be somewhat familiar with asymptotes. We'll spend a little time in the next lesson going into detail on these, but it's not a hole. Okay, it says I'm going along here, and I'm kind of going down here. I end up going down here infinitely. So it's not a hole, but there's actually an asymptote, a line that kind of graph is approaching but doesn't touch. Okay, some other things that we want to talk about are increasing and decreasing. Functions can be either increasing or decreasing as you read them from left to right. Okay. So if I'm looking at this first one, again, reading from left to right, as I'm going along, it seems to kind of be going up. So that would be an increasing interval. So again, when I'm saying going up, it's increasing in the y values as I read across the x values. And so this one here, as I follow the graph, as I move from left to right, the graph is going down. So this is a decreasing function. This one right here, as I move from left to right, it's not going up nor down in the y direction as I move left to right. So this one is just called a constant. It's got a constant interval. And then this last one, we're going to have actually a couple situations. As I read from left to right, it's certainly obviously going down until it gets to here. And then it's staying the same from here to here. And then as I read from left to right, it's going up here at the end. So this actual function actually has all three of these in there. It is actually increasing right here from 2 to infinity. All right, so if I look at that, I guess I put a little close bracket there because it does touch there, to infinity. It is constant on this middle part here. It's neither going up nor down, between -2 and 2, and it does touch that. So it's between -2 and 2. And on this part here, it's decreasing, from this negative infinity out until it hits -2. So that's where it's decreasing. It is from negative infinity all the way up to that -2, and it does touch it there. Okay. So again, just as a little notice, when we label the intervals above, when I did this, I'm only looking at those x values. I'm looking at how does it increase or decrease or stay the same as I read left to right on the x-axis. Really don't care about the y values in these intervals because that's the y value being told what to do by whether it's increasing or decreasing. Okay. All right, let's talk about some other vocabulary words here. Let's talk about boundedness. So what we're going to do is we're going to have functions that are either bounded above, bounded below, or they're just they're not bounded. It's just both. So we just kind of say it's just bounded, when it's both above and below. So when I'm looking at this first example, when I talk about bounded, I'm kind of looking at, does it have a place where it doesn't go any lower, it doesn't go any higher? Is there a maximum? Is there a minimum? We'll talk a little bit about that down here as well too. But when I'm looking at this first graph, assuming that this is all continuing upwards, it's got like at the very bottom, it doesn't go any lower than that. So what we do here is we say this one is bounded below. This one right here, it's got a little high spot right there. It's got a little low spot right there. So this is actually bounded on both above and below. So a lot of times we just say this is just bounded. The assumption is when you say it's bounded, it means that it's bounded both above and below. This one here, it's got a highest point right there, assuming that these again going on forever. This one would just be bounded above. So some other examples, it says draw a parent graph that is unbounded. Unbounded could be something like this. Just a linear equation that's just going infinitely down and infinitely up. Some of your cubics, that go like this, those lane changes, those are unbounded. Some of your logarithm functions, they go like this, are unbounded. Even your reciprocal or inverse functions, those are unbounded as well too, because they go infinitely down, infinitely up. All right, then let's talk a little bit about extrema. All right. So we've got a couple different things we've got to consider when we talk about extrema. We've got what are called absolute extrema. And, what I like to think about there is kind of simply that word absolute. What is the absolute highest point of that graph? Does it have an absolute highest? In other words, does it have a max? Or what's the lowest? Does it have an absolute minimum? Is there a place where it goes only that low and no lower? Then we also have what's called local extrema, or sometimes they're also called relative extrema. And those are sometimes within a graph, you've sort of got like a peak or a valley. Okay? So there might be just a little peak. That would be a local max, or a valley. That could be a local min. Let me kind of give you an example of each of those. This graph right here, if I look here, there's a high point right there. There's nothing else higher than that. So this graph has an absolute max. Okay? And if I look here, there's arrows here. This is going down forever and ever, down forever and ever and ever. So there is no absolute minimum, though some people kind of say, well, negative infinity would be the absolute minimum, but we just don't say that. We just say there is no minimum because it goes down forever. Where in this graph right here, okay, again, because this has got an arrow on the end, it's going up forever, it's going down forever. There is no absolute max, and there is no absolute min. But there are local minimums and maximums. And so if I look right here, that's a low point, but it's not the absolute lowest. This point right here, that's that point A. What I would say is A is a local min. And this B point right here, again, that's a high point. That B point is a high point, but it's not the absolute highest because it goes on forever over here. That B would be called a local max. And then, as I kind of explained over here, if I look at this one, kind of that same graph, if I kind of peek over here, this graph is not bounded. It has no extrema. So it's kind of what you say here. There's no extrema. Well, you could label it out and say there is no absolute max. There is no absolute minimum to this graph. So here, get a little practice. Draw a parent graph, an absolute minimum. I'm just going to take and draw one here like this. It's a little quadratic. Again, that would have an absolute minimum right there. We could look at, say, old absolute value graphs. Again, got a minimum right there. For that matter, some of the graphs we did in the last lesson, where we had the square root function. Again, that's an absolute minimum right there. Or if you even look at exponential growth problems, that kind of like this and shoot up, but when it goes back this way, it's just kind of leveling off at that horizontal asymptote. This one too would have a absolute minimum. All right, I'm going to move on here a little bit. Let's talk a little bit about symmetry. All right. So we're going to look at symmetry with respect to the y-axis. Again, to the y-axis. Looking at having symmetry about that y-axis. So again, basically what we're looking at is that we have the same thing on the left side that we do on the right side. That this line here, the y-axis, is like a mirror. All right. So if I've gone negative x units to the left, I'd be going positive x units to the right on those distances. Now, algebraically, what we're going to be looking at doing is basically proving this statement right here, which basically just says if I put in a negative value to the function, I will get the original function. And we'll practice some of that down below here. Just kind of putting those concepts together for right now. Numerically, what we look at, again, it kind of fits this idea here. I'm going to put a negative number in. I got that positive answer. Same thing here. When I put the positive number in, I get that same answer. So you can kind of see that symmetry. If I look through here, the left side giving the same number as the numbers I put on the right side, giving me that same number. All right. So if we do have symmetry with respect to the y-axis, we call these even functions. All right. The symmetry to the x-axis, kind of the same idea that now we're looking at the x-axis. And again, that we have what's ever on the top is the same as on the bottom. Right? So I think probably the best way to think about this one algebraically, don't think about this. I'm going to kind of give you the same kind of mathematical notation right here, and just kind of say that when we have that original function, we get out that same function when we put something in. Same thing here too, that when we start with the original function, we get also the opposite. So when I look at putting an x value in here, okay, this example happens to be 4. So if I put 4 in, I'll get a y value. But if I also put 4 in, I get the negative y value. Now, obviously, these aren't functions, but we can still have symmetry with respect to the x-axis, because here, if I'm putting in an x value, I'm getting two different values from an output. Right? And that's what we're just saying right there. Then there's symmetry with respect to the origin. A lot of times these here are just called reflection symmetries. Symmetry with respect to the origin is sometimes called rotational symmetry. Right? So graphically, what does that look like? Well, again, with respect to the origin, I'm going to look at the center here, that's 0, 0, and if I can spin it 180 degrees around the origin. So if I can take this point and go and spin it 180 degrees, I'd end up with the same thing. I'd end up with the same graph. Again, algebraically, what we look for is that when I put a negative value in, okay, so like here I'm going to put the negative x value in, I'll get this negative y value. But what it also means here too is if I put that negative x value in, I'll get the opposite of what the original function is. So again, we'll look at that in some examples down below. Maybe a table helps here a little bit too. That if I put a negative value in as an x value, I will get this is negative 3 put in, this would be negative 27. But if I do put the positive value in 3, I would get that positive value of y. Again, we'll practice that a little bit down below here to give a little bit more explanation on proving things are odd or even. Okay, but these are called odd functions. And if you can satisfy this statement right there, and we'll see how that works. So that's the big piece, is that, again, proving things algebraically that they're even, you're going to try to prove this statement. If they're odd, you're going to be trying to prove this statement. This is what I want to talk about here. It's just kind of getting that example in here. All right? So this is kind of what we're given here. So I kind of even like to write it out that way, to say given. So if we go back to the old geometry days, we get our givens that we write down. We're given this is f of x equals x squared plus 3. Right? Now if I look back up here, in both situations what we're doing is we're going to put in the negative value of x. We'll just see what comes out, right? And be able to compare that to see if it's an odd or an even. Okay? So that's the next thing I'm going to do in terms of my proof. Is I'm going to start with putting a negative value in and seeing what happens. So if I do that, if I put a negative x here into x, I'd have negative x, and I'd have to square it, and that's plus 3. If I kind of clean this up a little bit, negative x squared would just be x squared plus 3. And I've got that all simplified already. And if you notice, when I put the negative x in, I got this, which is the same as my original one. So in other words, this f of negative x, when I did that, gave me this. Or in other words, f of negative x gave me this original equation. And if I look up above, when I do that, situation here, I get to prove that this is an even function. So this would be an even function. Okay. Yeah, so let's give it another try. Let's do another problem. Let's do this one here. So again, I like to just start off, just keep myself organized, and write down what am I given. And I'm given that f of x, so you can substitute that for y, is is x to the third over 4 minus x squared. And then the goal is always, I'm going to start with a proof, and I'm going to put in a negative x for that x. So I'm just going to take that and put that in. Everywhere I see an x, I'm going to put negative x. So I'm going to put negative x in for that. So it's negative x. I'm going to have to cube that. It's going to be 4 minus, and I'm going to put negative x in for this x, and square that. All right. I clean this up a little bit. This piece here would still be negative x to the third. On the bottom here, this negative x squared becomes positive, so this would be 4 minus a positive x squared. And just to kind of clean it up a little bit, because I'm trying to see what happens here, is maybe some of you might be a little bit more comfortable just bringing that negative out front, just taking this negative and putting it out front. Really doesn't matter, you can keep it there. But maybe it just helps to see things a little bit more clearer, because if I look at this answer and compare it to my original one, it's not the same. And so I'm going to take f, put negative x in. When I look at this f of x, it's really just, there it is right here. It's this part right here is that f of x, but it's got the negative up front. Just do a negative f of x. And looking back up here, you can see when that happens, you've got an odd function. So what I want you to do is we'll end up having you pause the video here. I want you to practice these two on your own, and then come back and see the solutions and check your answers. All right, well, hopefully this is what you got for your answers for guided practice number 5. You can certainly pause this again and kind of double check your answers and your work. If you got any questions, certainly ask those in class. So we'll just continue on to the next part of the worksheet, and we'll talk a little bit about discontinuity. I told you we were going to revisit that a little bit. At the beginning, we talked a little bit about examples of discontinuity and having either holes. These are that holes. These two right here are holes. There's a hole there. There's a hole here. And this one was jump discontinuity, and this one here was an asymptote. But furthermore, we're going to talk about with discontinuity, is it removable or non-removable? So removable is just kind of like you're still going along with the continuity. It's a continuous graph, but just something has been pulled off and either just taken off completely or just put in a different spot. And that's kind of what this one's done. If I kind of go along, it's been taken out, put up here. So that's just removable. Same thing here, we're going to go along, point has been taken out, it's just been taken out, it's not been put anywhere else. So again, that's still just removable. This one's a little bit different, sometimes can be a little bit confusing. But as I go along, this point, it's not really removed. As I go along and kind of continue, it's just kind of been shifted up at that point. So that's kind of the way I like to think about that. So it's not really removed. This has been jumped up, so it's not removed, so we call it non-removable. And it's kind of the same thing with the asymptote. It's not something that's been removed. It's just somewhere where it just kind of can't be with that asymptote, so we call this non-removable. So algebraically, we want to talk a little bit more about this. And kind of give you a little definition for these problems. So a removable discontinuity or a hole, okay, occurs when you factor the denominator. So when I factor the denominator, it's one of those pieces, or for that matter, several of the pieces will cancel with a factor in the numerator. So let me show you what I mean. If I look at this top part, okay, there's not much I can do. That's just x plus 2. On the bottom, if I factor that, again, while we practice all that stuff with the prerequisite materials, so we can just go right to this and say that this is just x plus 3, x plus 2. Again, double check. 3 times 2 is 6, but when I add them, that's 5, so that works. The leading coefficient is 1. And then what I notice here is that this piece will cancel with that piece. Well, that's the key. When a factor in the denominator cancels with a factor in the numerator. So that x plus 2, this x plus 2 got canceled both in the numerator and the denominator. So I've got a hole. Well, where's that hole at? Well, if I set that canceled factor equal to 0 and solve, x equals 2 is where there is a hole. Okay. Now, leading into this next example, I look at this last piece right here at x plus 3. Okay. Well, when you factor the denominator, which is what we just did over here, an asymptote, so in other words, it actually should be a vertical asymptote, to be more specifically, occurs at the x value that makes the denominator 0. So I want to know, where does this x plus 3, when would that be 0? Well, if I solve that, it would be x equals negative 3. Okay, so this is where I would have an asymptote then. Let's practice this a couple times. Let's look at this. The numerator is still 2x. On the bottom, now that's the same factoring that we did over here. So that's x plus 3, x plus 2. And if you notice here, there's nothing on the top that cancels anything on the bottom. Now, if I had a little x out front here, that would certainly cancel, but I don't. So in regards to holes, there's none. I have no holes here. But the bottom here, if I look at this x plus 3, set that equal to 0, and let's take that x plus 2 and set that equal to 0, and solve. These are where I would have asymptotes. And again, vertical asymptotes, because it's x equals. Those are equations of vertical lines. So I have asymptotes at those two lines. So let's continue to practice. Take this x, we can factor this bottom part. And again, all the practice that we had over the years and reminders at the beginning of the year. X minus 2 and x plus 1. Negative 2 times 1 is negative 2. When I add those, negative 1. Great. Again, I notice I don't have anything that cancels with anything on the top and the bottom. Again, if I had an x out front, I would, but I don't. So I'm just going to look at that x minus 2. I want to know, when is that 0? That's x plus 1. When is that 0? If I solve it for each of these, that's where I have some asymptotes. Okay, well, I want you to try it on your own here, so we'll have you pause the video, work those problems out, come back, and double check your answer. All right, and hopefully as you work these out, you saw that this one doesn't have any holes. There's no canceling on the top and the bottom. It only has a couple of asymptotes. But this one over here, if you do a little factoring, notice that there was some canceling. So we do get a hole and then also an asymptote. So good work, everybody. What you should be able to do now is should be able to do these problems now on page 102. If you want some more practice, some additional practice, there are some available there as well.